Okay, so with that, we're going to go ahead and move into our next talk uh, it's great to have Rachel Locke back here. Many people have been asking me when the next episode of DSP Corner is going to be. For people who don't know what DSP Corner is, it's a place where Rachel has been giving her insights into the industry and creating some lessons for people that are looking to get more into the digital signal processing side of the industry without all of breaking down some of the technical jargon into easy to understand language. And Rachel is back to give her next episode, which is going to be on the Fourier transform, and she's going to be using Matlab for this. We're looking forward to having her back again. Thank you, Rachel, and take it away from here.
Hey, thank you, Josh. I always feel like you're saying that people have been asking you to hype me up because no one ever asked me personally, but maybe they feel more comfortable to approach you
Hey,
than
I
they
don't
do me.
know.
But yeah, thank you for all the positive feedback that I do get in the comments and the posts that I make about DSP Corner. It really means a lot to me that people are getting value from it. And that's why I continue to make the videos. Okay, let me try and share the screen. So yeah, thanks, Adam, for prompting us with those questions as well, because it really got me thinking about things, and it was a really useful exercise. And it got me thinking about why I started this series and why I continue to do it. And when I was developing this episode of DSP Corner, I considered leaving out the heavy mathematics of the DFT for fear of putting people off. But I realized that that is counterintuitive to the mission of this series. So this series is a sort of peace offering to myself and to others that have felt overwhelmed, disheartened, and felt that they just weren't cut out or didn't have the right education to learn digital signal processing, which was myself at many points in my master's degree. So I would be doing you a disservice if I didn't try and break down the essential mathematics that you'll need to become comfortable with if your goal is to work in a role where you'll need at least an understanding of audio DSP concepts. And yeah, I hope that people find this useful. And like I always say, I'm right at the beginning of my DSP journey. I'm not an expert, but I break things down in a way that I would have wanted when I was starting out. So let's get into learning about Fourier analysis in Matlab. Okay, so up first, we have the formula for the discrete Fourier transform. And the best way that I've found for building an understanding of these really quite gnarly DSP formulas is to break them down into digestible pieces and focus on first understanding those pieces of this puzzle before addressing how they relate to each other. So, like I said, here I've got the formula for the discrete Fourier transform. You'll know it's discrete because we're dealing with samples n and frequency bins k. And we've got square brackets. And for a continuous Fourier transform, you'll be dealing with integrals and integrating and integrating areas under a function. But this channel focuses on the digital side of signal processing, luckily, because I'm hopeless at integration. So what I've tried to do is break this down into 4 pieces, and we're going to try and understand the individual pieces before looking at how they relate to each other as a whole formula. So on the left side of the equation, we have this uppercase x of k, and this is the output of the discrete Fourier transform. And this is a complex output, meaning that we will have a real and an imaginary part. And rather than a sample index, K tells us the frequency bin number. So rather than samples in the output of our DFT, we'll have frequency bins. And the number of frequency bins will correspond with the number of samples in our input signal. The next segment, I think, is one of the two pieces of the puzzle that people find quite daunting at first, because it looks like a very unfamiliar mathematical symbol if you haven't seen it before. But this symbol in the middle there, like a sideways sort of M, is called sigma, so Greek letter sigma. And sigma basically means to sum. So it represents the summing of values over a given range. In this case, lowercase n is the sample number. Uppercase N is the total number of samples in our input signal, x of n, and the range n is defined from 0 to n minus 1. And in the example we're using, the signal is going to have 16 samples. So we're going to be summing over a range of n between 0 and 15, because it'll be 16 minus 1. And what sigma will have, what the summation will have, is it will have something to its right here. And basically what that will mean is we're summing whatever is here to the right over a range of whatever is defined on the bottom, that will be the beginning of your range, until whatever is defined on the top, that will be the end of your range. And I've just made a small example in Matlab to show how summation works. So I'm just going to jump over there and see if we can get that running. So Matlab has this, I think it's called a live script functionality, where you can, it's quite cool because you can put text and your code. So you can put in some examples of equations that you're trying to implement in code, or just anything that you're trying to figure out. You can also put some text about what it means. So again, I've put sigma means to sum. We sum whatever is to the right of sigma, in this case, the values of our signal x of n. The range of n, which we're required to sum over, is specified at the bottom and the top of sigma, where the bottom is the start of the range and the top is the end of the range. So in the example I've given here, you can see that we're going to be summing over the range 1 until n. And again, n is the length of our signal x that I've created here. And we've stored a variable for n as the length of x. And it may be a little confusing in terms of not starting at 0 up here, like we do in the actual DFT formula, but that is because Matlab indexes from 1. So we've decided to go with 1 because the first index of our array here will be the index 1 instead of index 0, which it is in other programming language. So yeah, just a little bit confusing and takes time to get used to in Matlab. And like I said, we're summing over a range, so a good way to implement something when a range is involved is to use a loop. So I've got a for loop here, and it's starting from n equals 1, and it's looping 5 times until n equals 5. And inside the for loop, we're going to be summing the elements of this signal x. And then at the end, we're going to print the sum. So if I run that, you can see that x has these values. The length is 5, and the sum is 66. So that's just sort of introduction to how summation works. We might have implemented it before, not known. But I think when you see it in a formula, it can look much more daunting than just summing over a range. So I hope that example helped you to understand summation if you hadn't seen it before. Just going to jump back to the slides for a moment. Cool. Yeah, so we were here. So yeah, we've just looked at this portion. So now we know we've got a summation, which is going to be from 0 until the length of our input signal -1. So it's going to have the same number of sums as the length of our input signal. The next segment is the input signal itself. We've seen this before when we looked at introduction to mathematical notation and signal processing. We can see that the input signal has an independent variable n, which is samples, and it's got the square brackets there to show you that it's a discrete input signal. Not too much more to say about our input signal. It's going to be, in our case, when we do the example, it's going to be a pure sinusoid input signal with 16 points. And I think maybe best to quickly show you that now before we move on to the most daunting part of this formula, which is called a complex exponential. And I think that's the one that trips people up the most. Definitely did for me anyway. And okay, I've tried to comment everything quite well here. So when the video goes out, it will be easy to relate back to and see what I meant in each line of code. And I will release the slides and the code as a companion for the talk as well, if anyone wants to have a go. Right, so first things first, I've given a sample rate, which is our samples per second that we're going to take. I've taken the period, which is the reciprocal of our sample rate. I always denote this as seconds per sample because it's how often we need a new sample based on what our sample rate is. I've given a duration, so I want a signal of 1 second, meaning that it will have 16 samples because there are 16 samples per second. I've given a frequency of 2, which is our cycles per second. So we're going to see 2 cycles in that seconds that we're going to plot, and that 2 cycles is going to be captured by 16 samples. I've created this time axis, which is what we're going to plot the values of our signal against. And then finally, I've created a cosine with the frequency 2, and we've put that time axis in there. Okay, I'm just going to run this. Maybe I'll comment out the FFT for now. Just comment out. Let's see how long it takes. That was surprisingly fast. Okay. So you can see that we have the general shape of a cosine wave here, and that is captured with these 16 lollipop samples that you can see on the plot. And this is a plot of amplitude over time, as we generally see in the time domain. And if I open up the command window, I plotted the values of our signal by just putting this line that says X. If you don't put a semicolon at the end of a line in Matlab, then it will print that value or those values to your command window. So I've just done that to show you that our signal is just a range of values, and it has 16 altogether. Okay, I'm going to jump back to, actually, I'll just show you one more thing in the workspace. When I was talking about the output of the DFT having k frequency bins and also having complex values, you can see, just close that down, that you have the FFT here. Okay, so this line, I'm actually calculating the DFT of our input signal X. And we're not going to do anything with it yet. I'm just wanting to show that we've got our input signal lowercase x, and that is 1 times 16, so 16 samples long. And you can see that uppercase X, which is the output of our DFT, also has 16 elements, let's say, and that they are complex. So that will be our 16K frequency bins, and they'll be complex numbers, meaning that they have a real part and an imaginary part. I don't know if I've actually covered this in any of the DSP Corner or whether it was in the workshop at ADC, but the real part of the output of the DFT is the magnitude. So how much the contribution of that frequency is at that bin. And the imaginary part is the phase information for that frequency. Hopefully I mentioned that before. We can look at that in more depth if people would like to, but hopefully it'll make a bit more sense when we look at the complex exponential just now. So I'm going to jump back over to the slides. Okay, I think we're back to where we were. I'll just point out as well that this complex exponential that we're about to look at, just get the highlight around it. This is something that I've written slightly in shorthand with the omega k. And down here, I've given what you would plug in if you wanted to write the longhand of this. So omega k is 2 pi over n, with capital N being the length of our signal, of our input signal. And quite often, if you're looking in textbooks for DSP or looking at DSP code, you'll have this, this practice of using lowercase letters for the time domain and uppercase letters for the frequency domain. And that's why we've got the lowercase x for our time domain input signal and the uppercase X for our frequency domain output. Cool. And because the complex exponential is quite complex, even that's not the exact meaning, I've dedicated a whole new slide to it. Okay. The discrete Fourier transform, how? So we're about to find out that the DFT is simply a point-by-point correlation of a discrete signal x of n, which is our input signal, with a collection of sinusoidal waves oscillating at frequency omega k. So omega is used to denote angular frequency, which we've looked at before, I think, when we were talking about sines and circles. So if you want to know more about converting between angular frequency and in radians and frequency in hertz, I think you can look back at the circles and sines video or the introduction to mathematical notation video on the channel. Okay, so what does it mean, point-by-point correlation of this signal with these signals? So x of n, like we said, is our input signal. And the reason we're doing a Fourier transform is we want to know about the frequency content of our input signal. And the way that we're going to find that out is by comparing it to base sinusoidal waves at different frequencies and seeing what the measure of similarity is between our input signal and some test signals, let's say. And if there is a strong positive correlation between them, then that will suggest that that frequency is present in some amount in our input signal. So this complex exponential that we've got on the side here, it has an exponent, which includes the complex number, or the imaginary number j, sorry, can also be denoted as I. It's got a frequency component and it's got a sample index n. Okay, so it's known as a complex exponential, and the multiplication of the input signal x of n with this complex exponential is what makes the output of the DFT complex. It looks daunting, but we can rewrite it in a more intuitive way. So there's someone called Euler who developed a formula, and it allows us to rewrite complex exponentials as its cosine and sinusoid components. So the one you'll see most often is this top one. E to the j x can be rewritten as cosine of x plus j sine of x. But you can see in our exponent, we've got a minus sign. So if we put the minus sign in there, all it does is it changes the sign from positive to negative. So we can rewrite our complex exponential as cosine of omega k n minus j sine of omega k n. And if you saw the episode on complex numbers, then you recognize that this is a complex number because it has a real part on the left and it has an imaginary part multiplied by the imaginary number j on the right here. And if I just jump back to the previous slide a second, whenever you see something next to each other in a formula like this, it means that they're being multiplied together. So I just spoke about how to find the frequencies present in our signal. We're going to do a correlation of our input signal with a collection of cosines, and it's actually going to be inverted signs because of the minus sign, to see what frequencies are causing a strong positive correlation between our input signal and the test signals. So this means a multiplication. So if we look at the formula as a whole, we're saying that for each frequency bin of our output, of our complex output, we're going to be summing over a correlation of our input signal with both a cosine element and an inverted sine element to see what the overall score is. I hope that makes some sort of sense. We're going to do a demonstration in Matlab and look at some animations that will hopefully make it a bit more clear. Okay, so the number of test signals that we're going to be multiplying our input signal against are going to be determined by the length of our input signal. And like it says here, number of base signals that are correlated with the input signal length. Here you can see a cosine component and an inverted sine component are generated for each frequency from 0 Hertz to 15 Hertz. And this correlates with our sigma summation that we saw before, where we had n equals 0 at the bottom and capital N, which is our signal length 16, minus 1 at the top. So a range from 0 Hertz to 15 Hertz. And I put the complex number up here, which is the cosine and the inverted sine component. So like I said, the reason that this sign is inverted comes from the minus sign out in front of our imaginary element here. And basically what's getting plugged in each time is this n. So it's going from 0 to 15. And as you can see, each time the GIF changes, the signal is going up 1 Hertz in frequency. Okay. This slide, there's a lot going on, so don't panic. We'll go through it step by step. I wanted to basically show what is the correlation process, like how does the DFT actually work? How does it determine what frequencies are present in our input signal? And we start off with the correlation. The lollipop stem signal you can see in orange here, or maybe red, is our input signal, x of n, which has 16 samples. The continuous or continuous looking wave, because nothing can be continuous in a computer, we can just give the impression of continuity by giving a very fine resolution. This is our cosine test signal. On the other side, we have, again, our input signal and the inverted sine test signal. And I've used the 2 Hertz one as an example because, as we know, that's the frequency that we're trying to find present in we're trying to verify that that is our input signal. It's a 2 Hertz sine wave, or cosine wave. So that's what we're trying to verify, that we're getting the right result for that one. And as you can see here, this is matching up very nicely. So that's what we would expect. And for the inverted sine, we can see that they have some points where they match. And we'll talk about why that is and why it cancels out. So the first thing that happens in the correlation is there's a point-by-point multiplication of the test signal with the input signal. And this causes a score, or it creates a new signal, let's say, of these 2 signals multiplied together. And this one below is that new signal. It's, if you can see, it's both signals are 1 at this point. 1 times 1 is 1, and about 0.7 here, times 0.7, which is down here, around 0.5, and so on and so forth. So this is our cosine correlation for 2 Hertz test signal. The next step is to sum all of these values together to give us an overall score of how present this particular frequency is in our input signal. So you can see that if you sum all of these together, you get this quite nice high score of 8 at the frequency 2, which is really reassuring because that's what we're expecting, a high score for frequency of 2. So we verified that our input signal and our test signal have really high similarity there. For our inverted sine, we can see, like I said, that there is some points that the test signal crosses through, but also that there's lots of points where it doesn't. And you can see when you create the signal of the correlation that it does have some points. But you can see that when you add these points together, they're going to cancel out because they're equal parts positive and equal parts negative. So when we do add them together, we get a result of 0. which is what we're expecting, 0 for all frequencies, because our input signal is a cosine, so we wouldn't expect there to be a sinusoid or a sine part in there. And then to get the total of the contribution of that signal, which we call the magnitude, we have to apply Pythagoras. And if you saw, I know I keep relating back to other DSP corners, but it's meant to be a sort of a continuation on one to another. So sometimes I won't go into something in so much detail because it's been covered before. But essentially, when I did the episode on complex numbers, I was saying that to get the magnitude of the signal, which relates to amplitude, we need to find the length of the hypotenuse of the Cartesian form complex number, and that was done by just rejigging Pythagoras formula to get the square root of a squared plus b squared. And in this case, a is our number over here, 8. B is 0 for this particular score, 2. So ultimately, for the 2 Hertz test signal, we get this overall magnitude of 8. And I'll just show you the code, which I wrote to generate these blocks. I'm on a sort of trial license at the moment of Matlab. So if anyone here works for Matlab and you fancy sponsoring DSP Corner, I'd be very grateful. So I think I've got about 2 hours left on the trial. But thank you very much for sponsoring my talk at ADC. Very much appreciated.
I'm sure we could convince Gabriel to do a comp license for this. He would be very happy with this.
Because otherwise, I'm going to have to keep creating email addresses, Gabriel. It's just just putting it out there. It's going to be trial after trial. Yeah. I mean, hopefully, I'll be earning enough at some point buy my own Matlab license, but I'm not sure we're quite there yet. Anyway, back to the talk. Where are we looking? So this one. I know there's quite a lot going on here, but when I put this code out, I'm gonna write a long README that will explain everything and why I've gone about it the way I have, because I found it very difficult to write an example of who'd have thought it, to write the DFT would be difficult. Obviously, it's not as complicated as the actual FFT implementation in Matlab, but it's just breaking down the steps of the correlation and the summation and everything that we've spoken about so far. So you can see that I've got, again, the same sampling rate, the same frequency of the signal that we spoke about in the other script. And what I've done is I've got a loop down here where I'm basically implementing exactly what we said on the formula, 0 to n minus 1 for n, lowercase n. And first thing we do is create these base sinusoids. So these are the sinusoids that we're going to be correlating with our input signal. And we saw them in the GIF that I made, where they're going up in frequency 1 Hertz at a time. So we've got the real part, which is the cosine, like we expressed before. And it has this variable n in here. And that n is changing on each iteration. So it starts at 0, and it goes all the way to n-1, which in our case is 15. And on each iteration, a different cosine and a different inverted sine are going to be created corresponding to the frequency that n is at that time. And then I plot them all to know about, might comment out this bit because it's about, well, it'll be 16 plots. But basically what I've gone for is plotting. Actually, I'm going to do it because I think it's a good way to visualize it. Let's see if it works. Oh, that's promising. Not seeing any plots yet though. Here we go. Something's happening. I'm like worried to press anything in case it freezes. Just giving it a second. Can we move to the side? Brilliant. Okay, so there's 16 plots here corresponding to the frequencies that I spoke about. This is how I created that GIF, more or less, with the different frequency test signals that we're using. This one is for 0 frequency. So as you can see, the continuous line has no oscillation whatsoever in this case. This one's at 1 because cosines always start at 1 at 0.0. And this one's at 0 because sinusoids or inverted sinusoids or sine waves. I keep saying sinusoids, but sinusoids can mean both cosines and sines. But yeah, it's easy to slip up with the terminology. So yeah, that's 0. And you'll see a trend here as we go through. That's 1 hertz. I've labeled them here. And you can see for the most part, there's not strong positive correlation here. They're not really hitting any points, or if they are, it's points that will cancel out once we do those next steps of the DFT formula until we get to 2 hertz, which is the one that we saw. And we do have that strong positive correlation for the cosine part. And yeah, it just goes on like that until all the way until 16, 15. Okay, I see what I've done. I plotted the correlation result over the last one, so these ones only got to 14. But yeah, there would usually be a 15 hertz one there. Okay, and this is the correlation result. And we can see that we have that value of 8 that we saw when we did the calculation for 2 hertz. We can also see something quite interesting, that we have another value of 8 for 14 hertz. And you might be thinking, how has this happened? Because our input signal was a single frequency sinusoid. So how so that it has 2 frequency components? We never added 14 hertz, so why is it there? Let's have a look in our next slide, why that might have happened. Okay, so I've got the plot here that we were just looking at, and I've highlighted the positive score for 2 hertz, which is what we're expecting. And I've also highlighted the positive score for 14 hertz, which is not quite what we were expecting because we never added this frequency to our signal. So why is it there? And I've never done a video particularly focusing on sampling theorem, but I think we must have touched on it at some point. But if you know anything about sampling theorem, you'll know that half of the sampling rate is called the Nyquist frequency. And because our sampling rate is 16, our Nyquist frequency is 8 hertz. And the sampling theorem states that you should have a sampling rate high enough so that none of the frequency components in your in the signal you're sampling are higher than this Nyquist rate. So they should all fall below 8 Hertz for the signal to be reproduced effectively, if you're thinking about analog to digital conversion and then conversion back from digital to analog. So we have our Nyquist frequency denoted here by the dashed line. And a phenomenon that we see is that a frequency that is present in our signal will be mirrored over the Nyquist frequency at the same distance as it was from the Nyquist frequency on the side, the left-hand side of the plot, let's say. So generally, all we're really interested in is this left-hand side of the plot, anything left of this dashed line, because this will not be audible. However, if we start having frequencies that are over the Nyquist rate in our signal, and we don't use a sampling rate high enough to account for those frequencies, then what we'll get, say we had one of 9, I should have really drawn this onto the graph, but just imagine there's a lollipop here. This will reflect back over the Nyquist frequency to create an audible new frequency that wasn't there in the first place in our signal. And that means we're actually adding harmonics, which isn't necessarily a good thing, but it's the way that a lot of distortions work, as you might know. And yeah, that's called aliasing. If you want me to do a video on aliasing, then let me know. But I think there are really good videos out there on aliasing, so I'm a bit, and sampling theorem, so I'm a bit hesitant to do that. But if you think it would work, let me know. And yeah, I hope that explains that plot. But on the right-hand side here, I basically included the reason that this is happening. You can see that, okay, on the 2 Hertz, as we expected, all the points of the blue wave, the test signal, are passing through the points of the input signal. But we also have this situation with 14 Hertz, whereby the test signal just happens to pass through all those points. And that is what causes us to have this result of thinking that this 14 Hertz is present in our signal. And I think, I'm not sure whether to do an actual FFT to verify that it's, yeah, let's do that really quickly. Just verify that, yeah, the FFT will produce the same result as what we've just looked at in my unusual implementation. So let's just verify that that works. Okay. So this is the same code as we saw in my implementation. Just I'll run it again so you can see the sinusoid. This is our cosine input signal sampled at 16 Hertz with a frequency of 2 Hertz. So when we take the FFT, I'll mention as well that there might be a bit of confusion between me using DFT and FFT. So the fast Fourier transform is an optimized algorithm of the discrete Fourier transform. And it's optimized for signal lengths that are powers of 2. So maybe next time we could talk about windowing and zero padding. And these are ways that we achieve lengths of powers of 2 of our input signals, if they aren't already, in order to make use of that optimization, and also to increase our frequency resolution, which means that we'll be able to see frequencies, differentiate between different frequencies in our FFT output more easily, and not have them sort of smear into each other and not be very easily individually distinguishable. So yeah, Matlab has the implementation of the FFT. So that's why, if there's any confusion between the two. Then I've also got this X mag and this X phase, and this is me grabbing the real part of the FFT output, and this is me grabbing the imaginary part of the FFT output. And like I said, the real part is the magnitude of the frequency present, and the imaginary part is the phase information of the frequency. So let me just uncomment this, and we'll have a look quickly before I finish. Okay, I actually might plot it instead of stem. Stem is just used to get those like lollipop style plots that we've seen throughout, but plot just uses straight lines, continuous lines. Okay, so first thoughts are, why is this at 3? We expected it to be at 2. And that's because these are our frequency bins. So our axis isn't yet in hertz. And I'm just going to show you quickly how to convert from frequency bins to frequency in hertz, so you can see accurately what frequencies are present in your signal. As we expected, we have this other peak, which will be the frequency mirrored over the Nyquist frequency. One thing that we can do, I said about phase information, say that we added a phase shift onto this cosine that we've got here, and the phase shift will be at the end here in the cosine calculation. Let's say 2.4. A cool thing that we can do is, if I run this again, we can verify that our phase information in our FFT output is correct, because I've calculated this X phase, which is our phase information, and we know that our peak is at frequency bin 3. So what we can do is grab the third element of our X phase. I could actually just do it in the command window. And we can see that that's 2.4. So that's the phase information that we're expecting. That's a good way that you can validate that. And I'll just show, if I can remember off the top of my head, how to convert from bins to frequency in hertz. I think it is. So we want an axis of 0 to n-1, but we want to multiply it by our sampling frequency divided by the number of signals in our input signal. I think that's right. Let's see. Anyone that knows, please correct me if it's wrong. See if that works. Do I have an n? Nope. This is like turning into one of Josh's live coding sessions. Me just talking to myself. Oh no, not normalized. Length of x. Okay. Let's see if this works. If not, I'll fix the code and get back to you. Oh, moment of truth. Yay! Now you can see that the frequencies are in the right place. So And it's the same as like my implementation. Everything worked out.
Fantastic.
I think I'm going to stop there because I was trying to pack too much into the talk. Yeah, I think I went on a lot longer than I planned. I hope that was useful, and thanks for listening as always.
Thank you very much, Rachel. I know that was very helpful for people online, and yeah, like we were saying, Rachel is back nearly every month, providing new lessons and demos on DSP fundamentals, and this is one of the essential ones. So thank you very much, Rachel, for doing this for us.
Yeah, thank you for having me. And I just wanted to quickly say that I saw in the chat, I think someone maybe called Wave, let me check. Wave Sequencer was saying that they would get major imposter syndrome if they were to give a talk. But I want them to know that I am a bag of nerves whenever I give a talk, and I just keep doing it and coming back time after time, hoping that one day I'll feel less nervous. And yeah, I just hope that inspires you to give a talk if you have an idea for one.
Absolutely.
Well, I'm going to stop sharing. Thanks very much.
Yes, thank you very much, Rachel.